We think we're so advanced. We have cranes that reach the clouds. We have computer-aided design that builds virtual worlds before a single shovel hits the dirt. We have materials engineered in labs stronger and lighter than anything nature ever made. We look back at the medieval period, the so-called Dark Ages, and we see mud and superstition and short, brutal lives. But then you stand in front of a cathedral, and you look up and up and up. The stone seems to defy gravity. The glass glows with colors we struggle to replicate. The whole thing has been standing there for 800 years, surviving wars, fires, and the slow grinding pressure of time. And you have to ask yourself, how? How did people with simple hand tools, with no electricity, with a grasp of mathematics we'd consider basic, build something that still takes our breath away? They didn't have steel. They didn't have reinforced concrete. Yet their buildings soared. The truth is, they knew things we've forgotten. They employed techniques born from necessity, perfected over generations, and passed down not in textbooks, but from master to apprentice. These weren't just tricks of the trade. They were profound understandings of physics, materials, science, chemistry, and engineering, all achieved through trial, error, and breathtaking intuition. Some of these methods were so effective, they seem like magic. Others were so simple and sustainable, we're only now rediscovering them in our search for a greener way to build. They were, in every sense of the word, ahead of their time. So, what were these lost arts of the medieval builder? What secrets are hiding in the stones of every castle and the timbers of every old barn? Number 17 was their secret code, hidden in cathedral blueprints. We start with something that wasn't a physical tool, but an idea, a system. When a modern architect designs a skyscraper, they use complex software. It calculates every stress, every load, every angle, down to 1,000th of a degree. A medieval master mason had a compass, a straight edge, and a set of ratios. And with these, they created some of the most complex and beautiful buildings in human history. They didn't have blueprints as we know them. They had something more like a guiding principle, a geometric key. This was the practice of ad quadratum and ad triangulum. The concept is simple at its core. Ad quadratum means from the square. The entire design of a building, from its overall footprint to the size of its pillars and the arch of its windows, could be derived from a single square and its geometry. You start with a square, you then rotate it 45 degrees and place it over the original. The points of this new square give you a new set of proportions. You can create smaller squares inside or larger ones outside, and the relationships between them all remain harmonious. It's a system that creates what we might call a visual rhythm. Nothing looks out of place because everything is related back to that original simple shape. The historian and architect John James has spent decades studying French cathedrals, measuring them stone by stone. His research suggests that these masons used this geometric system to lay out everything, ensuring a coherent design even when the building took centuries to complete and different masters took over the job. The blueprint was the geometric rule, not a detailed drawing. Ad triangulum worked the same way, but with the equilateral triangle. This shape was seen as a symbol of the Holy Trinity, so it had spiritual significance as well as practical use. It was used to determine the pitch of a roof or the elegant point of a Gothic arch. Otto von Simpson, in his landmark book, The Gothic Cathedral, argues that these geometric and mathematical relationships weren't just for looks. They were a form of theology. Building a cathedral with these divine proportions was a way of creating a model of heaven on earth. The building itself became a form of prayer. This knowledge was closely guarded. The medieval stonemasons' guilds were secret societies. They didn't write everything down. Knowledge was passed verbally from master to apprentice. The only real glimpse we have into their methods is from a handful of surviving sketchbooks, like the one from the 13th century French master Villard de Honnecourt. His drawings are filled with figures and buildings, all based on simple geometric shapes. It shows a mind that saw the world through a lens of geometry. This was ahead of its time because it was a form of algorithmic design. They had a simple set of rules that could generate infinite complexity and harmony, all without advanced mathematics or computers. It was a system that was both deeply practical and profoundly spiritual. It ensured structural integrity and aesthetic beauty at the same time. We lost this intuitive approach when the Renaissance shifted focus to classical Roman and Greek ideals of proportion and the guild system slowly faded away. We started relying on precise written plans instead of shared, memorized principles. But what if we've completely misunderstood the purpose of these geometric games? Were they really just about divine proportion, or did they contain hidden structural rules that we no longer recognize? Could a mason look at a series of nested squares and instantly know how thick a wall needed to be? And what other systems of knowledge, passed down by word of mouth for centuries, died out completely without ever being written down? Number 16, how did they build without nails? Walk into an old timber-framed barn or house. Look up at the massive beams that form the skeleton of the building. You'll see huge pieces of oak, bigger than anything you could buy at a lumber yard today. And then you'll notice something strange. There are no nails, no metal plates. The entire structure is held together by wood alone. This is the art of mortise and tenon joinery, a technique so precise and durable that these buildings are still standing perfectly straight after 500 years or more. The concept is simple. A mortise is a hole, usually square or rectangular, cut into a piece of wood. A tenon is a tongue cut on the end of another piece of wood designed to fit perfectly into the mortise. Once the tenon is slid into the mortise, a wooden peg called a trunnel or dowel is driven through a hole drilled through both pieces. This locks the joint in place. It sounds straightforward, but the genius is in the details. Medieval carpenters were masters of wood. They understood it intimately. They knew that wood expands and contracts with changes in humidity and temperature. A metal nail would resist this movement, causing the wood to split and crack over time. A wooden joint, however, moves with the wood. The entire frame can flex and settle slightly without weakening. The oak pegs were often made from wood that was drier than the main beams. When the peg was driven in, it would absorb moisture from the beams and swell, creating an incredibly tight, permanent fit. A 2010 study by the University of Bath's Department of Architecture and Civil Engineering examined the structural properties of historic timber joints. They found that these peg mortise and tenon joints were remarkably resilient, able to withstand stress and flexing in ways modern rigid joints cannot. The complexity was astonishing. They didn't just have one type of joint. There were dovetail joints, scarf joints for joining beams end to end, and complex tying joints for where multiple beams met at the roof's apex. Each was chosen for the specific type of force it had to resist. Cutting these joints required immense skill. Everything was done by hand with saws, chisels, and augers. The carpenters would often prefabricate the entire frame of a building on the ground. They would cut every joint, fit every piece together, and mark them with a unique set of symbols, often Roman numerals called carpenter's marks. Once they were sure everything fit perfectly, they would take it all apart, transport it to the building site, and reassemble it in a process that could take just a few days. This was modular construction, centuries before the term was invented. This technique was ahead of its time because it was a perfectly sustainable and incredibly durable system that worked in harmony with the nature of the material. It required no industrial manufacturing, no metal smelting. It just required deep knowledge and skill. We forgot this technique for a simple reason. The Industrial Revolution gave us cheap, mass-produced nails. It was faster and required less skill to just nail boards together. The art of the master joiner, who could spend days cutting a single complex joint, became too expensive and slow. But as we look at these ancient structures, we have to ask some questions. Did the carpenters use specific types of wood for the pegs to create a chemical reaction with the oak beams that hardened the joint over time? You know, we know they understood tannins in okay. What else did they know? And could we ever truly replicate the skill of someone who learned to read the grain and tension of a piece of wood? Not from a book, but from a lifetime of touch and feel. Number 15. Could a wall without glue be stronger than one with it? Imagine building a wall with nothing but stones. No cement, no mortar, no glue of any kind. It sounds unstable, temporary. Yet all across the medieval world, from the field boundaries of Ireland to the terraced hillsides of Peru, people built dry stone walls that have lasted for 1,000 years. This technique is ancient, but medieval builders perfected it, turning it into a science of friction, gravity, and intuition. A dry stone wall is not just a pile of rocks, it's an intricate interlocking puzzle. The builder or waller has to choose each stone carefully, seeing not just its face, but its shape, its weight, and how it will sit with its neighbors. The basic principle is to always place a larger stone, so it rests on two stones below it, bridging the gap between them. This is called harding. It prevents straight lines of weakness from forming in the wall. You never want joints to line up vertically. The real genius is in the wall's cross-section. A well-built dry stone wall is actually two separate walls leaning against each other. The space in the middle is tightly packed with smaller stones. This internal structure is crucial. It adds weight and stability, and through the wall, at regular intervals, the waller places through stones. These are long, flat stones that go all the way from one side of the wall to the other, effectively tying the two faces together and preventing them from bulging outwards. The top is finished with a layer of copestones, often placed vertically and packed tightly to weigh everything down and protect the inner core from rain. What makes this technique so far ahead of its time is its resilience and environmental harmony. A wall with mortar is rigid. When the ground shifts or it's pushed by floodwater, it cracks and fails. A dry stone wall is flexible, it has thousands of tiny gaps, it can move and settle without breaking. Water can pass right through it, which is why it's so effective for building retaining walls on hillsides. The pressure of water buildup, which would destroy a mortared wall, is simply not an issue. Research from organizations like the Dry Stone Walling Association of Great Britain has shown how these structures create unique microhabitats for plants, insects, and small animals, making them a living part of the landscape. We forgot this skill because of concrete. Portland cement, invented in the 19th century, made construction fast and easy. Where anyone could mix a bag of cement and slap stones together, the slow, patient art of fitting stones by hand, a skill that took years to master, seemed obsolete. It was cheaper to build a rigid wall that would last 50 years than a flexible one that would last 500. But this lost art raises questions. We understand the basic physics, but did the master wallers have rules of thumb about the specific weight and shape of stones that we haven't yet quantified? Was there an acoustic element tapping the stones to hear their density and predict how they would settle? And what is the absolute limit of this technology? Without mortar, could you really build a castle? Some ancient forts suggest you could. Number 14, how did they build so high with only wood and rope? Look at the spires of Salisbury Cathedral. They reach 404 feet into the sky. It was the tallest building in the world for over 250 years after its completion around 1320. Now, imagine building that with no steel scaffolding, no powered lifts, no cranes as we know them. The scaffolding they used to build these stone giants was an architectural marvel in its own right, a temporary wooden skeleton that grew with the building. Medieval scaffolding wasn't the metal grid you see today. It was built from straight timber poles, often fir or pine, lashed together with rope. The real ingenuity was how it was integrated into the building itself. As the stone walls went up, the builders would leave small, square holes in the masonry called putlog holes. The horizontal poles of the scaffolding, the putlogs, would be inserted into these holes. This meant the stone wall itself supported the scaffolding. It was an incredibly efficient system. It didn't require a massive, freestanding structure built from the ground up. The scaffolding literally climbed the building as it was built. When the building was finished, they would simply remove the putlogs and, in many cases, just leave the holes. You can still see neat rows of putlog holes on the sides of countless medieval castles and churches today. They are the ghosts of the construction process. For building the high vaults and roofs, they would construct massive timber structures called centering. This was a curved wooden frame that would support the stones of an arch or a vault until the final keystone was put in place. Once the keystone was set, the arch became self-supporting, and the centering could be carefully lowered and removed. Designing and building this centering was a complex feat of engineering. If it was too weak, it would collapse under the weight of the stone. If it was too rigid, it would be impossible to remove without damaging the arch. The historian Jean Gimpel, in The Cathedral Builders, describes how these construction sites were hives of organized activity, with master carpenters and masons working in a carefully choreographed dance. The scaffolding wasn't just a platform to stand on. It included ramps for wheelbarrows and tracks for simple carts, all designed to move heavy materials up to the working level. It was a temporary vertical city, all made of wood and rope. This technique was ahead of its time in its efficiency and integration. By using the building itself as part of the support structure, they saved enormous amounts of timber and time. The modular, adaptable nature of the pole and rope system meant they could build around any shape, from a curved apse to a soaring buttress. We abandoned this method for steel scaffolding because it's stronger, more uniform, and can be assembled faster by less skilled labor. The rope lashing was replaced by standardized metal clamps, but the precise methods they used remain partly a mystery. How do they calculate the exact amount of give needed in the centering for a massive vault? We find few plans. Was this knowledge also part of the mason's oral tradition? And when they built the huge timber frames for the roof high above the stone vaults, were these assembled piece by piece in the air, or were they built on the ground and hoisted into place whole? The logistics are mind-boggling. Number 13, could a bridge power a city? Old London Bridge was not just a way to cross the River Thames. For nearly 600 years, from its completion in the early 13th century, it was a marvel of medieval engineering and a bustling hub of life. It was covered in houses, shops, and even a chapel. But underneath, hidden between its massive stone piers, was a technology that was centuries ahead of its time, an integrated, tide-powered industrial complex. The bridge was built with 19 pointed arches, but they weren't all the same size. This, combined with the wide stone piers, or starlings, that protected the foundations, created a bottleneck. The powerful tides of the Thames would rush through these narrow gaps at incredible speed. It was essentially a man-made series of rapids, and medieval engineers saw this not as a problem, but as an opportunity. They built water wheels into the arches of the bridge. These weren't the gentle, overshot wheels of a country mill. These were powerful undershot wheels driven by the sheer force of the current. At first they were used for a simple but vital task, grinding corn for the city's bakers. But in 1582, a Dutch engineer named Peter Maurice installed a far more sophisticated system. His water wheel powered a set of pumps that drew water from the Thames and forced it through a network of wooden pipes, providing the first piped water supply to parts of London. This system was so successful that it was expanded and operated for over 200 years. There were also wheels that powered bellows for forges and machines for making textiles. The bridge was a factory. This was an extraordinary example of multifunctional, sustainable infrastructure. They took a piece of civil engineering, a bridge, and turned it into a power source for the city's water and industry. This concept of embedding energy generation into infrastructure is something we're only now re-exploring with things like tidal lagoons and solar roadways. The engineers of London Bridge were doing it 800 years ago. Their understanding of hydrology, while not expressed in modern formulas, was clearly profound. They knew how to channel the power of the river to do useful work. The technology was eventually forgotten, or more accurately, superseded. The Industrial Revolution brought a much more powerful and reliable source of energy, the steam engine. Steam-powered pumps made the water wheels of London Bridge obsolete. When a new, more modern bridge was built in the 1830s, the old, cluttered industrial bridge was torn down. The idea of using a bridge to power a city was lost. This leaves us with some tantalizing questions. Were there detailed calculations and models made to determine the optimal placement of the water wheels, or was it all done by trial and error? How did they manage the maintenance of these complex machines in the fiercely corrosive, constantly moving environment under the bridge? And were there other similar projects on a smaller scale on other medieval bridges that have been completely lost to history? Number 12. Did they use clay pots to tune a cathedral? Step inside a great Gothic cathedral. The sound is different. Your voice doesn't just echo, it blooms, it resonates. The stone and glass create a unique acoustic environment. For centuries, people believed this was just a happy accident, a byproduct of the building's vast size and complex shape. But what if it was intentional? What if medieval builders had a secret technique for fine-tuning the sound of a room, using simple clay pots? This is the theory of the acoustic jar or resonant pot. Scattered across Europe, from Sweden to Spain, hundreds of medieval churches have been found with ceramic pots embedded high up in the walls or in the vaults of the ceiling, with their mouths opening into the church. The Roman architect Vitruvius mentioned the use of bronze or earthenware resonators in ancient theaters to clarify and enhance the actors' voices. The theory is that medieval builders rediscovered or continued this practice. How would it work? It's based on a principle called a Helmholtz resonator. You can see this effect when you blow across the top of a bottle. A specific low note is produced. The pitch of that note is determined by the volume of air inside the bottle and the size of the opening. By embedding jars of different sizes into the walls, the builders could, in theory, create a series of resonators. These wouldn't make the room louder. Instead, they would absorb sound energy at their specific resonant frequency. This could be used to damp down annoying echoes or booming frequencies that would muddy the sound of the choir's chant or the priest's sermon. It would be a form of passive acoustic treatment, shaping the sound of the space. The evidence is controversial. Some scholars, like the archaeologist and musicologist Dr. Paolo Vittori, have championed the theory, pointing to the deliberate placement of the jars in acoustically significant locations. In a 2012 study, researchers from the University of Salford used computer modeling to simulate the acoustic effect of these jars in a virtual church. Their findings suggested that the pots could indeed have had a subtle but noticeable effect on the acoustics, particularly in reducing the reverberation time at certain low frequencies. So, why is this a forgotten technique? If it worked, why did we stop? The practice seems to fade out after the 16th century. It could be that changes in church music with the introduction of complex polyphony and powerful organs made the subtle effects of the jars less relevant. Or perhaps the knowledge was simply lost as the old builders' guilds declined. The most common counter-argument is that the pots had no acoustic purpose at all. They might have been used to lighten the load of the vault, or they were simply symbolic, or even just a convenient place for birds to nest. The debate continues, leaving us with intriguing questions. If the pots were for acoustic purposes, how did the builders know what sizes to use and where to place them? Did they have a sophisticated understanding of resonant frequencies achieved through experimentation? Could they clap or sing a note and know, just by listening to the echo, exactly where a resonator was needed? And are there other, even stranger acoustic devices hidden in the walls of old buildings, mistaken for mere decoration? Number 11 was stained glass, a form of ancient nanotechnology. We think of stained glass as art, a beautiful picture made of colored glass. But to the medieval craftsman, it was also a form of high technology. It was chemistry, physics, and engineering all at once. The vibrant, luminous colors of the glass in a cathedral like Chartres in France, created in the 12th and 13th centuries, are so pure and stable that modern science has struggled to understand how they were made. The secret lies in what we would now call nanotechnology. To create colored glass, you add metallic oxides to the molten sand and ash. Copper oxide makes a ruby red. Cobalt makes the famous deep blue of Chartres. Manganese makes purple, and iron makes green or yellow. But medieval artisans didn't have pure, refined metals. They were working with impure ores, and they had no way of precisely controlling the temperature of their wood-fired furnaces. Yet they achieved results of stunning clarity and permanence. Recent scientific analysis using electron microscopes has revealed their secret. For example, to make a rich ruby red glass, they used copper oxide, but if the copper particles are too large, the glass looks muddy and opaque. The medieval glassmakers somehow figured out how to create nanoparticles of copper, tiny spheres of metal only a few billionths of a meter across, suspended within the glass. These nanoparticles interact with light in a very specific way, scattering the blue and green light and letting the red light pass through, creating a brilliant pure color. The famous Lycurgus cup, a Roman artifact from the 4th century, does something similar with gold and silver nanoparticles, appearing green in reflected light and red in transmitted light. It seems medieval artisans perfected this ancient technique. The blue glass of Chartres is another mystery. They used cobalt, but the local cobalt ore was full of impurities like nickel and arsenic. Modern glassmakers would consider this unusable. Yet, as researchers like Patrick de Gries at the University of Leuven have shown, it was these very impurities, combined with a specific type of wood ash they used as a flux, that created the unique, stable, and dazzling blue that has not faded in 800 years. They had developed a recipe that turned a dirty, raw material into a perfect finished product. This was ahead of its time because they were manipulating matter at the nanoscale without ever knowing it. They were practicing a highly advanced form of materials science through observation, tradition, and countless failed experiments. Stained glass wasn't just decorative. In the massive open structures of Gothic cathedrals, the vast walls of glass were also structural elements. They filled the space between the stone ribs, acting as a weatherproof skin. The lead cames, the H-shaped strips that held the pieces of glass, formed a flexible web that could withstand wind pressure. This knowledge was largely lost after the medieval period. The secret recipes passed down within families of glassmakers faded away. Later attempts to make colored glass often resulted in colors that were less vibrant or that faded over time. The rise of clear glass and painting on glass with enamel also reduced the demand for the old pot metal glass where the color was part of the glass itself. This leaves us wondering, how did they control the size of the nanoparticles? Was it a specific temperature, a specific cooling time, or a secret ingredient they stirred into the pot? Did the different types of wood they used for their fires impart specific chemical properties to the glass? and what other impurities in their raw materials were actually the secret ingredients to their most incredible creations. Number 10. How can a staircase be a weapon? In a medieval castle, the great spiral staircase wasn't just for getting from one floor to another. It was a death trap. It was a brilliantly designed piece of defensive architecture, using simple geometry to give a massive advantage to the person at the top. Most spiral staircases in castles turn clockwise as you go up. This is not an accident. Think about how you fight with a sword. Most people are right-handed. As a defender coming down a clockwise spiral, your right arm, your sword arm, has a wide, open arc to swing. The central pillar of the staircase is on your left, out of the way. You can slash and stab downwards with full force. Now, think about the attacker coming up the stairs. Their right arm is cramped against the central pillar. They have very little room to swing their sword. Their shield, held in their left arm, is also less useful because the main threat is coming from their right, where their vision is partly blocked by the curve of the wall. The defender has the high ground and the freedom to move. The attacker is in a narrow, deadly funnel. The design was even more clever than that. The steps themselves were often deliberately uneven. Some would be slightly higher, some slightly narrower. The defenders, who lived in the castle, would know the quirks of every step. They could move quickly and confidently in the dark. An attacker storming up the stairs in a panic would be constantly stumbling, breaking their rhythm, and making them an easy target. The central pillar, the newel, was also sometimes designed to be much wider at the base and narrower at the top, further restricting the movement of those at the bottom. This simple design principle, documented by architectural historians like Mark Morris in his books on medieval castles, is a perfect example of how every element of a castle was designed with defense in mind. It was a form of passive defense, a weapon built into the very fabric of the building. Some castles, like those owned by the Kerr family in Scotland, who are famously left-handed, have staircases that spiral counterclockwise, giving the advantage to a left-handed defender. This shows how deliberate and customized the design was. This technique was ahead of its time because it was an early form of ergonomic design applied to warfare. It was a deep understanding of human biomechanics and how to exploit them in a combat situation. It was a simple, low-tech solution to a complex tactical problem. Why was it forgotten? Because castles became obsolete. With the rise of powerful cannons in the 15th and 16th centuries, castle walls could be breached easily. Sieges became less about storming up staircases and more about artillery bombardments. The internal architecture of buildings no longer needed to be a weapon, but it makes you wonder about the other subtle design tricks built into these castles. Were the heights of arrow slits calculated to match the average eye level of an attacker at a specific distance? Were the acoustics of gatehouses designed to amplify the sound of approaching horses? Were there secret visual cues in the stonework, invisible to an outsider, that signaled safe passages or hidden traps to the castle's inhabitants? Number 9. What if you could rain fire from the floor? When you imagine defending a castle wall, you probably picture soldiers dropping rocks or pouring boiling oil on the attackers below. But this was messy and dangerous. You had to lean far out over the battlements, exposing yourself to enemy arrows. In the later medieval period, they came up with a much better solution: machicolations. A machicolation is an opening in the floor of the battlements between the supporting stone brackets, or corbels. It's essentially a purpose-built hole for killing people through. From the safety of the wall walk, defenders could drop anything they wanted: rocks, heavy objects, boiling water, quicklime, even dead animals, to spread disease directly onto the heads of anyone trying to scale the wall or break down the gate below. This was a major innovation over an earlier, less permanent version called hoardings. Hoardings were wooden structures that were temporarily built out from the top of the walls during a siege. They served the same purpose, but they had a major disadvantage: they were made of wood. Attackers could set them on fire with flaming arrows. Machicolations, being built of stone as part of the main wall, were fireproof. They were a permanent, integrated part of the castle's defenses. The introduction of machicolations, which became common in Europe in the 14th century, radically changed the dynamic of a siege. It made the base of the wall, previously a relative blind spot, the most dangerous place for an attacker to be. The design was clever. The corbels that supported the overhanging parapet were not just functional, they were often decorative, adding an aesthetic rhythm to the top of the wall. But their main job was to create these deadly gaps. The gatehouse, always the most vulnerable part of a castle, would be heavily machicolated. Sometimes there would be a whole series of them nicknamed murder holes along the ceiling of the entrance passage, allowing defenders on the floor above to attack any invaders who managed to get through the first gate. This technique was ahead of its time because it was a simple, elegant solution that solved multiple problems at once. It provided superior protection for the defenders, created a more effective field of fire, and was more durable than its wooden predecessor. The military historian R. Allen Brown emphasized that innovations like machicolations were as important as any weapon in the balance of power between attacker and defender. So why did we forget it? For the same reason as the spiral staircase cannons. Once artillery could reliably blast holes in the main curtain wall from a distance, the fight at the base of the wall became less important. The fortifications changed with low, thick, angled walls designed to deflect cannonballs rather than tall, thin walls designed to stop climbers. Machicolations became purely decorative elements on later buildings, a stylistic nod to a bygone era of warfare. But looking at them now raises questions. Were the sizes and shapes of the machicolations standardized, or were they customized based on the height of the wall and the expected type of attack? Did they develop specialized projectiles designed to tumble or shatter in a specific way when dropped through the holes? And how did the defenders coordinate their attacks through these holes when their own visibility was so limited? It's number 8. Can you build a skyscraper out of dirt? We think of mud and earth as primitive building materials, weak, temporary. But medieval builders in many parts of the world, particularly in arid regions, used a technique called pièce de terre, or rammed earth, to create massive, durable structures that have stood for centuries. The Great Walls of the Alhambra Palace in Granada, Spain, built largely in the 13th and 14th centuries, are a testament to the power of this forgotten art. The process is simple in concept but requires great skill and practice. You take soil, not topsoil, but subsoil with the right mix of sand, gravel, and clay, and you add a small amount of water. Not enough to make it mud, just enough to make it damp. Then you dump this mixture into a temporary wooden formwork like a large bottomless box. And then you compact it, you pound it down layer by layer with heavy wooden tampers. The pressure forces the particles together, squeezing out the air and creating a dense monolithic block that is as hard as stone. Once one section is complete, you move the formwork up or along and repeat the process. The finished wall is a single massive piece of man-made sedimentary rock. The builders of the Alhambra were masters of this. They knew exactly the right mixture of soil to use. They often added a stabilizer like lime or even animal blood to increase the strength and water resistance of the material. The finished walls were so strong they could support multiple stories and heavy tile roofs. They also had incredible thermal properties. The thick earth walls absorb the sun's heat during the day and slowly release it at night, keeping the interior of the building cool in the summer and warm in the winter. It's a natural, passive form of air conditioning. A 2017 study published in the journal Construction and Building Materials analyzed the physical properties of historic rammed earth from the Iberian Peninsula and found it to be a remarkably durable and thermally efficient material, well suited to the local climate. This was a technology far ahead of its time. It was a sustainable, low-cost building method that used locally sourced materials. It had a tiny carbon footprint compared to firing bricks or making cement. The walls were breathable, preventing problems with damp and mold. It was a perfect example of architecture that was in harmony with its environment. So why was it forgotten, at least in the Western world? The rise of industrial materials like brick and concrete, which could be standardized and used by less skilled labor, pushed rammed earth to the margins. It was seen as primitive and old-fashioned. But as we search for more sustainable ways to build today, rammed earth is making a comeback. And this forces us to ask what the medieval masters knew that we don't. How did they test the soil to know if it had the right clay to sand ratio? Was it by feel, by smell, by taste? What were all the different organic additives they used, and how did they change the properties of the final wall? And what was the true upper limit of this technology? Could you build a cathedral from dirt? Number 7, how did they get central heating before electricity? The idea of a warm floor on a cold winter morning seems like a modern luxury. But the Romans had it figured out 2,000 years ago with their hypocaust system. And while the full complexity of the Roman system was largely lost after the fall of the empire, a simpler and cleverer version of it persisted and evolved in medieval monasteries and castles. It was a way of using a single fire to heat an entire building. The Roman hypocaust was a complex underfloor furnace. The floor of a room was raised up on a series of short pillars called pillae. Hot air and smoke from a furnace outside the building would be fed into this crawl space, heating the floor from below. The hot air would then be channeled up through hollow tiles in the walls, heating them as well, before exiting through a chimney. It was an incredibly effective, but also incredibly expensive and labor-intensive system. Well, medieval builders adapted this idea into something more practical. In monasteries, for example, there was often a single large fireplace in a room called the warming room or calfactory. This was usually the only heated room where the monks were allowed to gather. But the builders were clever. This fireplace was often located directly below the monks' dormitory, the dorter. A section of the dormitory floor would be made of stone or tile. The heat from the fire below would rise and warm this section of the floor, creating a zone of radiant heat that would take the chill off the entire room. In some castles and great houses, they developed a more advanced channel system. Ducts, lined with stone or tile, would be built into the thickness of the walls and floors. These ducts would run from a large fireplace in the basement or great hall to other rooms in the building. For hot air and smoke from the fire would be drawn through these channels, heating the mass of the stone walls along the way. The walls themselves would then become giant, slow-release radiators. The Cluny Abbey in France, a hugely influential monastic center, had a sophisticated system of ducted heating in the 11th and 12th centuries. The flue gases from the kitchen and bakery fires were channeled under the floors of other buildings to provide warmth. This was ahead of its time because it was an integrated, energy-efficient HVAC system. They were capturing and using waste heat. They understood the principles of thermal mass and radiant heating. They knew that a warm wall feels more comfortable than a blast of hot air. This knowledge was lost with the advent of the simple, inefficient open fireplace in every room, and later, with the rise of cheap fuel for boilers and furnaces. It became easier to just burn more fuel than to design a clever, integrated system. This makes us wonder about the full extent of their knowledge. Did they design the ducts to create a natural convective loop, with cool air being drawn back towards the fire, creating constant circulation without any fans? How did they clean out these inaccessible channels, and were there more advanced systems, perhaps using steam or hot water from the kitchens, that we have completely overlooked, mistaking their pipes and channels for drains? Number 6, could your walls breathe? Today we seal our houses in plastic wrap and insulation. We make them airtight to be energy efficient. But this can lead to problems with condensation, mold, and poor indoor air quality. The medieval builders of common houses had the opposite approach. Their walls were designed to breathe. The primary material for this was a simple, cheap, and surprisingly effective composite called wattle and daub. Wattle and daub was the standard infill material for timber-framed houses across Europe for centuries. The wattle was a lattice framework of thin, flexible wooden strips, often hazel or willow, woven around the upright timber studs of the wall. It looked like a giant, sturdy basket. The daub was sticky plaster made from a mixture of clay or soil, water, a binding agent like animal dung, and a reinforcing material like straw or animal hair. This daub was then smeared all over both sides of the wattle, pushed into the gaps, and smoothed flat. Once dry, it was often coated with lime wash, a type of paint made from lime and water, which acted as a protective, breathable sealant. This simple wall system was genius. First, it was made entirely from cheap, local materials. You could find everything you needed within a few miles of your building site. Second, it was a brilliant combination of materials. The wattle provided tensile strength, like the rebar in concrete. The daub provided compressive strength and thermal mass. The straw or hair acted like a fiber reinforcement, preventing the daub from cracking as it dried. A 2005 conservation study by Historic England analyzed the properties of historic daub and found it to be a remarkably complex and well-engineered material. But the most forward-thinking aspect of wattle and daub is that it's hygroscopic. This means it can absorb moisture from the air when humidity is high and release it when humidity is low. The clay and lime in the wall act like a natural dehumidifier and humidifier, keeping the indoor environment stable and comfortable. The wall literally breathes, managing moisture and preventing the buildup of damp that plagues so many modern buildings. We forgot about wattle and daub when solid brick walls became the standard. The bricks were seen as more permanent, more fire-resistant, and a sign of wealth. Later, we moved to cavity walls and plasterboard. The old breathable mood and stick construction was seen as something to be ashamed of. We tore it out and replaced it with modern, impermeable materials, often trapping moisture in the old timber frames and causing them to rot. Now, as we look for sustainable, healthy building materials, we're rediscovering the wisdom of wattle and daub. But what did the old builders know that we've yet to relearn? Did they use specific types of soil from different locations for different properties? What was the full range of additives they used in their daub? We know about dung and straw, but did they use things like cheese whey, egg whites, or specific plant saps to improve its performance, as some historical texts hint? And could they tune the mix to be more insulating or have more thermal mass, depending on which side of the house the wall was on? Number 5. What if a roof was grown, not built? A thatched roof is one of the most iconic images of the pre-modern world. We tend to think of it as a poor, primitive roofing material. But a well-made thatched roof was a highly sophisticated, long-lasting, and remarkably effective piece of technology. The craft of the master thatcher was one of the most skilled trades in the medieval period. Thatch is not just a pile of straw on a roof, it's a carefully constructed system of layers. The thatcher would tie bundles of material, typically water reed, long straw, or combed wheat reed, onto the timber roof structure, starting at the bottom and working up. Each new layer would overlap the one below it, like tiles. A good thatched roof would be at least 12 inches thick. The key to its effectiveness is that water doesn't soak through it. Because the reeds are laid at a steep angle, water runs down the outside of the stalks from one layer to the next and drips off the eaves. Only the top inch or two of the thatch ever gets wet. Underneath it remains bone dry. And a professionally thatched roof made from good quality water reed could last for 50 to 70 years. It was also an incredible insulator. The thick layer of hollow-stemmed reeds trapped air, keeping the house warm in winter and cool in summer. While modern studies, such as those conducted by the Building Research Establishment in the UK, have confirmed that thatch has excellent thermal insulation properties, often outperforming modern materials. It was also surprisingly heavy, which helped to hold the timber frame of the house down in high winds. The thatchers developed a whole range of techniques for finishing the ribs at the top of the roof, often creating beautiful decorative patterns that were the signature of a particular craftsman or region. This was a technology ahead of its time because it was the ultimate in sustainable, locally sourced building materials. The reeds were a renewable crop, often harvested from local wetlands. The roof was fully biodegradable at the end of its life. It was a breathing structure that helped to ventilate the roof space, preventing the buildup of condensation. We lost this technology for two main reasons. First, fire. Thatch can burn, and as towns and cities grew more crowded, the risk of a fire spreading from one roof to another led to regulations banning its use. Second, the availability of cheaper, mass-produced materials like slate, clay tiles, and later, metal sheeting made thatch seem like a slow, labor-intensive option. But the revival of thatching for historic and eco-friendly buildings has shown us how much we've forgotten. How did the thatchers know which reeds to cut, and at what time of year to maximize their durability? Did they treat the reeds with anything, like a soak in a salt marsh, to make them more fire-resistant or less appealing to pests? And what about the complex geometries of thatching around chimneys and dormer windows? How were these skills involving complex three-dimensional thinking passed down without any written diagrams? Number 4, how do you make a stone ceiling? One of the defining features of Gothic architecture is the ribbed vault. You walk into a cathedral and your eyes are drawn upwards to a complex skeletal web of stone that spiders across the ceiling. It's beautiful, but it wasn't just for decoration. The ribbed vault was a structural revolution, the key that unlocked the height and light of the great cathedrals. You know, it was a way to solve an enormous engineering problem. Before the ribbed vault, builders used the simple barrel vault, which was essentially a continuous round arch like the inside of a tunnel. A barrel vault is strong, but it's also incredibly heavy. All that weight presses straight down and outwards on the walls, meaning the walls had to be massively thick with only tiny windows. It created buildings that were dark and heavy. The ribbed vault changed everything. The builders realized that the structural forces in a vault were not spread evenly, but were concentrated along the diagonal lines. So they built a skeleton first. They constructed thin stone arches or ribs running diagonally from the corners of a bay and across its center. This created a strong framework. Then, they simply filled in the web like panels between the ribs with much thinner, lighter stone. It was a revolutionary idea. All the weight of the vault was now collected by the ribs and channeled down into specific points on the pillars below. The walls in between the pillars no longer had to carry any weight. They could be opened up and filled with vast stained glass windows. This is what gives Gothic cathedrals their sense of lightness and grace. The development of the ribbed vault, starting around the year 1100 at Durham Cathedral in England, was a process of rapid innovation. Masons experimented with different patterns, from the simple 4-part quadripartite vaults to more complex 6-part sexpartite vaults, and eventually to the incredibly ornate fan vaults of the late Gothic period. Each was an attempt to distribute the weight more efficiently and create a more elegant visual effect. As Robert Mark from Princeton University showed with his pioneering work in photoelastic modeling in the 1970s, these medieval builders had an incredibly sophisticated, intuitive understanding of structural mechanics. Their designs were not just decorative, they were highly efficient engineering solutions. This technology was light years ahead of its time. It was a modular skeletal construction system made of stone. It allowed for greater height, more light, and more complex floor plans than anything that had come before. We forgot it because architectural styles changed. The Renaissance went back to the classical forms of domes and barrel vaults. And then the development of steel frame construction in the 19th century provided a completely new way to build tall, light-filled buildings. The complex art of cutting and setting the stones for a ribbed vault became a lost skill. But huge questions remain. How did they lay out the complex three-dimensional curves of the ribs? They must have used full-scale templates on a tracing floor, but the geometry involved was immense. How did they construct the wooden centering to support these complex shapes during construction? And was there a sonic component to their design? Did they understand that? By breaking the ceiling into smaller panels, they were also breaking up sound waves and improving the acoustics of the building. Number 3, why do Gothic cathedrals look like skeletons? From the outside, the most dramatic feature of a great Gothic cathedral is the flying buttress. These are the graceful, arching arms of stone that leap from the outer walls to a series of heavy piers. To a modern eye, they can look like decoration, or maybe a sort of stone scaffolding that was never taken down. But they are the secret to the cathedral's height. They are the external skeleton that holds the whole building up. As we saw with the ribbed vault, the new Gothic style channeled all the weight of the roof and vaults onto a few specific points. This created a huge problem. The outward thrust from the stone vaults was immense. It was constantly trying to push the tall, thin walls over. The traditional solution was to build thicker walls, but that would defeat the whole purpose of creating a light-filled space. The flying buttress was the elegant revolutionary solution. Instead of fighting the outward thrust with dead weight inside the building, they caught it in midair. The thrust from the high vaults would be transferred through an arch TV, the flyer show across open space to a massive stone pier on the outside of the building. This pier, often weighed down with a decorative pinnacle on top, would then safely direct all that force down into the ground. It was a brilliant counterintuitive idea. It turned the building inside out. The structural support was now visible on the exterior, leaving the interior as a vast, open, uncluttered space. This system, first used in a major way at Notre Dame de Paris in the late 12th century, allowed builders to go higher and higher, with ever thinner walls and ever larger windows. Engineering was astonishingly precise. The angle of the flyer had to be just right to catch the thrust from the vault. Sometimes they used a double flyer system, one to catch the thrust from the high vault, and a lower one to counter the pressure from the wind on the vast roof. This was structural engineering of the highest order, all worked out without computers, through a combination of geometry, scale models, and some terrifying full-scale trial and error. There were collapses. The first choir at Beauvais Cathedral, which aimed to be the tallest of all, collapsed in 1284, partly because the buttresses were too far apart and too slender. The builders learned from their mistakes and rebuilt. The flying buttress was ahead of its time because it was a pure, honest expression of structural physics. It was a machine for directing forces, and its form was dictated entirely by its function. We lost the need for this technology when new materials like cast iron and structural steel allowed us to build tall frames that could resist these forces internally. The buttress became redundant, but we are still left with so many questions about the minds that created them. How did they calculate the forces involved? We know they didn't use modern mathematics. Did they use hanging chain models, as some have theorized? A chain hanging in a catenary curve perfectly mirrors the ideal compression arch when inverted. How did they account for variables like wind load or the settling of the foundations over decades? And was the aesthetic, the beautiful rhythmic march of the buttresses around the building, a happy accident, or did they deliberately shape these raw engineering components into something that would also lift the human spirit? Number two, was Roman concrete better than ours? This one is a bit of a cheat because the secret wasn't invented in the medieval period. It was invented by the Romans, but the reason it's on this list is because it was so far ahead of its time that after the Roman Empire fell, the secret was completely forgotten for over 1,000 years. And medieval builders, for all their genius, could never replicate it. Roman concrete or opus commencium was a miracle material. The Pantheon in Rome, with its 142-foot unreinforced concrete dome completed around 128 AD, is still the largest of its kind in the world. Roman harbors and breakwaters, built with concrete poured directly into the sea, have survived 2,000 years of constant battering from the waves. Modern concrete structures in the same environment can begin to crumble in a few decades. So, what was their secret? Recent scientific breakthroughs have finally given us the answer. A team of researchers from MIT and Harvard, publishing in the journal Science Advances in 2023, discovered that the Romans used a hot mixing technique. Instead of just mixing slaked lime with water, they used quicklime, a more reactive, unslaked form of lime. When water is added to quicklime, it creates a powerful exothermic reaction, heating the whole mixture. The researchers found that this process created unique mineral formations that gave the concrete a remarkable ability to self-heal. When tiny cracks formed in the concrete over time, rainwater would seep in and react with these leftover lime clasts, creating new calcite crystals that would fill the crack and heal the structure. The medieval mortar, by contrast, was a much weaker substance. It was typically just a simple mix of lime, sand, and water. It worked perfectly well as a binder for stone blocks, but it didn't have the monolithic strength or the incredible durability of the Roman formula. The knowledge was lost. The specific volcanic ash the Romans used, called pozzolana, which was crucial to the chemical reaction, was not widely available or understood outside of Italy. The complex chemistry and the hot mixing process were part of a sophisticated engineering tradition that simply vanished with the empire. For centuries, builders could only look at the colossal Roman ruins with a sense of wonder and inferiority. This technology was so far ahead of its time that we are only now, in the 21st century, fully understanding its chemistry and trying to replicate its self-healing properties to create more durable, sustainable, modern concrete. The Dark Age was a very real thing when it came to the science of cement. This raises some profound questions. What other Roman chemical technologies were lost? Were there recipes for waterproof plasters, fireproof coatings, or even flexible mortars that disappeared completely? How did the Romans discover this precise and complex chemical process? Was it a single lucky accident or the result of a long, systematic research program that we have no record of? And what are the chances that medieval alchemists, in their search for gold, accidentally stumbled upon similar powerful chemical reactions, but, failing to see their practical value, never wrote them down? Number one, what was the most powerful machine of the Middle Ages? It wasn't a trebuchet, it wasn't a windmill. The most powerful and important machine of the medieval building site was also the simplest. It was the treadwheel crane, or magna rota, and it was powered by the most readily available energy source of the time people. This machine was the key to building the great cathedrals. It was the only way they could lift the massive stone blocks, timbers, and lead sheets hundreds of feet into the air. The design was simple and brutally effective. It consisted of a large wooden wheel, perhaps 15 feet or more in diameter, with a walkway inside it like a giant hamster wheel. One or two men would walk inside the wheel. Their weight and movement would turn the wheel, which was connected by an axle to a winding drum. A rope would wind onto the drum, pulling up the load. It was a simple human-powered engine that used the principle of the lever to multiply human strength. According to the research of Gene Gimple in the Cathedral Builders, a single person walking in a treadwheel could lift about 1,000 pounds. Two men could lift nearly a ton. This was a massive leap in lifting capacity compared to simple pulley systems or muscle power. The cranes themselves were often ingenious structures. They were built on the ground and then hoisted up and assembled on the rising walls of the cathedral. Sometimes they were built into the timber structure of the roof and simply left there after the building was finished. Several of these original medieval cranes still exist, hidden in the attics of cathedrals like Salisbury in England and Beverley Minster. Seeing one today is like finding a dinosaur fossil. It's a relic of a lost world of construction. The operation of these cranes required skill and courage. The crane master would use a system of signals to communicate with the workers on the ground. The men on the wheel had to walk at a steady pace, and crucially, they had to be able to stop the wheel precisely and hold the load steady, sometimes for long periods, while the masons on the scaffolding maneuvered the stone into its final position. They used a simple but effective pawl and ratchet system, or a basic brake to do this. It was dangerous, physically demanding work. This machine was ahead of its time because it was a perfectly optimized piece of human-powered technology. It was a simple, elegant solution to the single biggest challenge of vertical construction. It was easy to build and maintain using the skills and materials of the day. It was far more powerful than any animal-powered lifting device. The treadwheel crane was the unsung hero of the Gothic age. We forgot about it with the invention of the steam engine and then the electric motor. Machines became infinitely more powerful, and the idea of using a person as the engine became obsolete. But as we look at these surviving cranes, we are filled with questions. What was the true limit of their lifting power? Are the surviving examples typical, or were there even larger, more powerful versions that have been lost? How did they manage the complex rigging and the potential for ropes to snap under such immense loads? And what does it say about the people who walked in those wheels, day after day, slowly and patiently raising a cathedral stone by stone towards the heavens? What did they think about walking for hours inside a giant wooden circle with the fate of their fellow workers hanging on their every step?